what do we want to get? We want to get a lower bound on OPT. Okay. So what is the natural lower bound on OPT? So Mr. Goel had made an observation previously. Let's look at that observation once again. So this observation he made. He said that if the number of tasks is even less than the number of people to do the tasks, then what will happen is nobody will get more than one task. Then the largest task, that means the task with the maximum length, is going to be the max load anyway. Right? So the task with longest length cannot be avoided when somebody has to do the longest load, highest load task. So that is definitely lower bound on OPT, isn't it?
Yes.
So the task having the highest running time, having the highest load. So the max load task is a lower bound on OPT. So OPT is at least so let us also have some notation. Let us say that there are m let us say there are m students or m people do the tasks and n tasks. I think we already had this notation. So did we say that Ti is the time required to do that ith task? Yeah, so here, so let us say the time to perform the ith task is Ti. Okay. So ith task requires Ti time. So I know for a fact that somebody has to do the task with highest duration. So OPT is at least this quantity. This is a lower bound. This is the first observation. So far, so good.
Yes.
Okay. What else can we say?
So this is only for the minimization problem, and for the maximization, it would be a fraction kind of thing. Like say, in this case, it is written as say it's greater than or equals to 4 of this thing. So for maximization, it would be 1/4 kind of the thing.
Yeah, let us only focus on the problem at hand, which is a minimization problem. And you are right, the maximization problems will have a symmetric description, and everything that I'm going to say about minimization problems, similar things can be said about maximization problems.
Okay.
So are we in a position to say that this algorithm that Suhas has suggested? So let's look at what we want to do. So let's look at we have run this algorithm of Suhas. What is step 1? Sort. Step 2, welfare maximization. Sorting in decreasing order, and then giving the task at hand to the person who is least loaded at that point. So let us say we consider that student who has the maximum load under this algorithm. After we have executed this algorithm, we identify that there is this fellow, student I, he has the maximum load on him. So can we see that the load of, okay, so under this distribution, okay. So let us simplify things. Let us say that we have this distribution only, which Suhas's algorithm has suggested, and Li denotes load on student I. So are we in a position to say that the load that this algorithm has suggested, the max load Li, is not more than, let us say, 2 times OPT? Are we in a position to say just by looking at this observation that Mr. Goel had made?
We can, if the sum of the remaining weights is sum of the remaining task is less than this quantity. I have another observation that while allocating tasks to the remaining students, we should assign loads by so first we need to compute the distance of the loads of the remaining students from this the largest weight, and then we should assign the remaining task to the students. So how far one student's load is from the maximum load, and whether the upcoming load, so greedy kind of the strategy kind of the thing, that whether the remaining load can be, remaining task can be assigned uh, to that student or not, such that the maximum load of the remaining student should not cross the maximum load, uh, just to avoid such a situation to the extent possible.
But are you not saying the equivalent thing? So both these two steps we have are greedy steps. In the first step, we are processing the tasks in decreasing order of load. So the max load task, that max duration task is processed before anything else. And then we are maximizing welfare also. So we are saying that we identify that student who is least loaded and we give the next job to that student. So we are also maintaining that, okay, this student is very far off than the max load student in terms of load.
Yes, but then there is a slight change that if we find the load of another student and which is still less than the maximum load, and wherein the new task can be accommodated, then let us give preference to that student. Uh, like in this case, we are assigning this load to the second student because it has the next minimum thing. But then, so mine policy would be slightly different from this. Probably I'm unable to explain the things properly, but
No,
I'm
so
unable
how are you going to process this set of
yeah.
tasks?
So the first six is there, and then the second is okay. So second is four is okay, and then the third is third, and that is, so third cannot be accommodated to the S2, so therefore third is all right. And now the two is remaining. So now the second student is 2 units away from the max, and third is 3 units away from the max, and the task is two. So let us give the preference to S3 in the hope of accommodating one more uh, task in case if that task requires 1 unit of the time. And the second last one is 2. So the distance of S3 from the max now is 1. So this cannot be accommodated. The distance of S2 from S1 is now 2. So I include this here. And now the last is remaining, carries the, so now I have no other option left except that I need to include it to X3. Probably for other values, this policy may make a slight difference, wherein I am
Okay.
using the maximum load as a yardstick.
Okay, fine. I think that is probably there is a good policy, but right now I'm not able to see how these two policies can lead to distinct distributions. But for the sake of time, let us take that question offline. We will let first analyze that this algorithm that first sort the task in decreasing order and then maximize welfare by assigning the next job to the least loaded student. Let us see how it is a two approximation.
Yes.
So another observation needs to be made to say a statement like this. Okay, let's see that observation. So we want to say a statement like this. So we have already observation one. So observe that uh, mm, uh, you have distributed the loads to n students. Okay, so you had n students, and you have total duration of tasks, which is summation I from 1 to n ti. This was the total duration of tasks that you had to perform, right? But you had only n people to do this much man hours or man days. So by pigeonhole principle, at least one student should do the average amount of work, right? Should get this quantity. Let us call this quantity T. That is a total uh, number of. This is a total time. This is a sum of all times, all the times for all the tasks. So at least one student must get T by N load. Is that easy to see?
Yes. Ceiling of T-value. Yeah.
Let us not worry about ceiling and course now. I mean, we can take care of these things. But you are right, let us not worry about it now. But if nobody gets T by N load, everybody gets less than T by N load, then how would N people be able to do T task, that T amount of task? That is not possible, right? So are you with me? To give it a thought for another minute, maybe, that the total amount of task, the total amount of time to carry out these N tasks is summation Ti. Now only N people can be given the tasks. So at least one person has to do Ty N task. Otherwise, how will so much work get done?
It's because we cannot leave any person empty. Otherwise, we won't be minimizing the maximum.
Yes. Yes. No, if the number of tasks is less than the number of people, then that is the trivial case. Everybody will get one or less number of tasks. Then whatever is the max duration task, that is the max load. In that case, we have a optimal solution.
Yes.
So here we will assume that the number of tasks is more than the number of people. So at least one person is getting more than one task. And now with this observation at hand, we have the second statement that OPT's second lower bound is that OPT is at least T by N. That no matter what the distribution is, even the optimal algorithm will be forced to have one person doing T by N amount of task. This is the second observation. So far, so good.
I have one doubt. Shouldn't it be T by M?
You are saying T by আমাদের student, we have M students, right? Oh, I was
Yes.
okay. So fine. I was thinking that N is the number of people. Yeah.
Because you have defined T in this way that you have n tasks.
Yes.
Capital T.
Okay. I made a silly mistake here. So I should write. So since in this place, so here I had made the mistake. So initially I said there are M students and N tasks. Then I was distributing the tasks to N students only. So that's where I made the mistake. Thanks for pointing out, Kostov. Okay, at least Kostov is hearing with attention. Yeah, so far it looks good. Is there any other issue? This looks okay. Okay, so now let's consider how to sort of compare the load that we are reporting, max load that we are reporting. So SI is the max load student as per our algorithm, this algorithm, let us say. So we are reporting a max load of Li. So now we want to say that Li is at most 2 OPT. This is what we want to say. With the exploitation of these two observations, observation 1 and 2. Any ideas?
Sir, on a similar line of thought, can we also say that maximum of Li will be less than the optimal, or less than equals to optimal time taken to do that?
Maximum of Li. So max of Li, max is over what?
Maximum is over over I. Maximum for all I, maximum of Li.
Yeah, so that is what the inequality you are suggesting.
It is less than the total optimal, less than equals to the total optimal time taken.
What's the meaning of total optimal time?
I was thinking along the lines that when you told that at least one student should get T by M load, like this is all, like this might seem like a trivial thing, but I don't know if it will help in the proof or not. Also, some student must process the most time or read the most time consuming paper.
That is this observation. Observation 1.
Oh, okay. Right, right.
So some students should read the most lengthy paper, most time consuming paper, and some student must also read the average amount of time to read the papers. So that's all we have in hand. And we want to say that the way we have done the allocation, the load on the max load on any student is at most 2 times the max load on a student if we could do it optimally. We are not putting the student under a lot of undue pressure. It's just that we are not able to do the assignment optimally because of inherent hardness of the problem. Okay, so let's look at the solution. So this guy, student I, has the max load as per our allocation. So now student I, if he has received only one task, so then we have an optimal solution. So as per our mechanism distribution, if he has received only one task, then whatever that task is, the TI is less than equal to max this thing, and we know that is less than equal to OPT. So we have done the optimal distribution. So let us say this has received multiple tasks. This student has received multiple tasks. Many tasks he has received. It's very unfortunate. Oh, so let's say ordering is also important, right? So it must have received tasks in decreasing order because of the way we have defined the algorithm. So it cannot receive a larger task after a smaller task. Is this all right? That this gradation, this assignment order is also in decreasing order for the student.
Yes, all right.
Okay. So now consider the last task it has received. So the length of that task is at most the max load, at most this quantity, the maximum time consuming task. So this task alone, so I am considering this task alone. So this piece is at most OPT. This piece is at most OPT. This is by observation 1. Okay. Now, what is the contribution of the rest of the tasks?
Is Li minus OPT.
Yes. I mean, I want to say it in, let's be more. Let's say we call it, this thing is, and let's say tau. I mean, let's say tau is the duration of the last task it has received. Then the rest of the task is Li minus tau. Okay. So now we have to say that how Li minus tau is also less than OPT. That is our target. Our target is to prove that Li minus tau is also less than OPT.
I think we can use different index variables for tasks and students.
Okay. Oh, I see. So you mean LJ I should put? That's what you're saying?
Yes, yes, like whatever is convenient.
So tau is less than OP2, that is clear. The other, this observation we have to use somehow, that okay, so now before the M, so before the last task was assigned, so we had n tasks before the last task was assigned. So at that point, the average load on any student was T by M minus 1. So therefore, the load on this guy would have been, just a second, I'm slightly getting confused here. Okay. So LJ, we want to say LJ minus tau is equal to T by M. And then we will get LJ minus tau is at most OPT. So the question is, how does this step follow? Okay. Okay, so now I get it. So see, yeah, so when this task was assigned to SJ, so at that time SJ was the least loaded student. Okay, so that means everybody else had at least as much load as SJ at that time. So that is how the average load was more than LJ minus tau. Sorry for confusing. I will write it more. So I'll do it once again. Sorry for confusing. I'll do it freshly. So this is SJ, the one who has got the maximum load. Now what happened? This has got these tasks. Let's take a different color. Sorry for confusing you. So the tasks were given like this: the larger task, second larger task, and so on. Then this is the last task. So there is no confusion that this last task, which is taking tau duration, and this overall is LJ. The rest of the things is LJ minus tau. Okay. So since tau is one of the tasks, it is at most the largest task. So max Ti. and therefore it is at most OPT from observation 1. Observation 1 OPT says that the max task is at most OPT. Okay. Now we wanted to argue that this is also at most OPT. So how to do that? So consider the moment this tau duration task was given to the student. So at that point, every other student, what was the load on every other student? It was more than the load of this student. That is the reason our algorithm gave that task to SI. So everything else was at least as much as LJ minus tau. So all these things was at least LJ minus tau. Otherwise, this student wouldn't have got tau. Do you understand?
Yes.
Okay. So therefore, the average I want to use this operation, I'll just copy it. So at that time, when tau was added, the total time of the jobs or tasks, I'll say, tasks that were assigned, that are assigned till then, is some t dash. So the t dash is at most t, because t is the sum of all the tasks taken together. So now this t dash by the at the time, let us say n dash tasks are given. So that average, so is LJ minus tau is the smallest guy. So the smallest load thing is less than the average. Okay. So I'm using n and m again. So let's make it m dash. So let us say m dash tasks have been assigned till then. Okay. So now this average. So consider that this average can only grow. Okay. So when you are adding more, so m dash is equal to m, right? So you want to see the average over every student. So average over all students at that time. So the average can only grow. So that is how LJ minus tau is at most OPT. Okay, I think I did not do a good job in explaining this, but if you ask me questions where you didn't get it, I will be able to make things more clearer. So that is how this is also at most OPT. That is how we have a two approximation. I'm sorry, but if you tell me where exactly there is doubt, I will explain that part again.
So what this T prime here is?
Okay, so T prime is the total time of the tasks that are assigned till this guy gets assigned to SJ. So you are assigning tasks one by one. So at some point, the student SJ is assigned this task, which has length tau. So till then, whatever tasks have been assigned, the sum of the durations of those tasks is T prime.
Okay. So is this the second last assignment of the task or what?
Second last assignment meaning?
So meaning is that since this task LJ minus tau has been assigned to rest everybody else, and now the only last task is remaining, and which has been assigned to SJ. And so which made the optimal solution worst by an amount of tau. Is this the case or?
Yes, so it might have happened that after this task gets assigned to SJ, some more tasks were still waiting to be assigned, and they were assigned to other students, not this student. So the task assigned to this student at the end was this task. So
Okay.
beyond that, there could have been tasks, but they were assigned to other people.
Right.
So now, since you know that T dash is less than T, because at most, so if there are other tasks, then the total sum of tasks would have been more than the total sum of tasks you have seen so far. So that is how T dash is at most T. So now you want to say that, okay, what is the average load on any student at this point when this task has arrived for assignment? So that average load is T dash by M. But at this point, when this task gets assigned, this student was the least loaded. So everybody else was more loaded than this student. And therefore, the load on the student, which is Lj minus tau, couldn't have been larger than the average at that time. So that is why the smallest load is at most the average load, which is T dash minus by M, and which is at most T by M because of this inequality. And that is at most OPT by our observation 2.
Yes.
Indranil, you have understood what I said. I think
Yes, sir. So Lj minus tau should be less than 1 by m over all L. Suppose
yes.
k goes from I to m, and then that we basically proved in observation 1, so we can directly say that Lj minus tau is less than OPT.
Yes. But I was not very eloquent. I mumbled anyway. But if you understood, it's good. But if you have any component of the proof, if you are not comfortable with, I can explain it again.
Yes, sir, I got that.
Great. Usaf, are you good?
Yes. Since tau is at most OPT, so we can say that Lj is at most twice OPT.
So this part you are okay, right?
Yes.
Thank you. So I had to practice. I did not rehearse it. Sorry about it. So I think I'll do a better job next time. Anyway, so we can start. What is the last component of today's session is feedback and Q&A. So I think we have had enough today. Let us go to the last component. If you have any questions or feedback to give me, please feel free to do so.
There are some questions at the chat box.
Oh,
You can see.
these questions were added long ago. I think this fellow might have left. Shishir, are you there?
Yes, I am. But
Okay, so
things you clarified later. Thanks.
Okay, okay. I'm sorry, I didn't do a good job today. Anyway, so
So how
next,
did you explain that this problem is NP hard?
oh, I did
Yeah,
not prove.
lost at
I
that
did
point.
not. Okay. So I did not prove that this problem is NP hard. I just made a comment that this problem is NP hard. So one person pointed out that this problem is similar to other NP hard problems, which are subset sum and knapsack.
Okay.
And I said that this is also NP hard, but there is a formal proof of it. Means to prove that a problem is NP hard, you have to take an existing NP hard problem, a known NP hard problem, and prove that this known NP hard problem is equivalent to the problem that you are considering. But I did not do that exercise.
Okay. Okay. And this is all discrete, right? It is scheduling this work assignment problem. So we
Yes.
will the last function that you wrote, it will always move in steps. We will never have a functional equivalent that continuously changing. For example, say there is a work stream continuously coming, and we have to assign the next task to a free student or NQ it, and still maintain the global optimal.
Yes.
Look at this.
So observe that what you were saying, that if you do not know beforehand that what is the next item in the stream, that if you do not know that the next task is going to take how much time, and only when the task arrives, you are going to make a decision where it should be assigned. Even then, this two approximation argument that you are not going to do any poorer than 2 times OPT is valid, because nowhere in the proof we have used the fact that these tasks were sorted beforehand. So there was no pre-processing step that we have exploited in the proof. So we did not need to say that, okay, because these tasks are in some order, that is why we are saying that this is at most OPT and this is at most OPT. So this two approximation is even valid in the streaming setup.
Okay.
And in this, I'll make a comment that since we did not exploit the step 1, that is the sorting step, which cannot be done if the setup is streaming. If you exploit this sorting step, then this analysis can be tightened, and one can also prove a 3/2 approximation. But that is not possible in the streaming setup. In the streaming setup, 2 approximation is the best for this algorithm.
Okay.
Thanks for the question. All right, so tomorrow is Sunday, and tomorrow we are going to meet in the morning. So many people are not available on Sunday. The least amount of attendance is, so we have this form, and the percentage of people who are ready to come on Sunday is the least when compared to other days. So we'll start at 10:30 and we'll not stretch very far. So I think in 2 hours or so, we should be able to finish. So if you have time, you can join, and we will see some other problems. So the plan is visibility problems, but even before visibility, maybe some covering problems would give the basics. So I think covering followed by visibility would be a better flow of exposition. So there could be a change from visibility to covering tomorrow. Okay, I think there are no more questions. If there are no more questions, then I'll thank all of you again for joining.
Siddharth,
Yes, yes.
about the last class, so you shared the blog, the Medium blog.
Yes.
I had a question. So if my distance is not Euclidean, will it work? That is, if I am working on lattice graphs where all are Manhattan distances, can I still use the median-based partitioning
So you were
to
saying
get the
that
closest plane?
so you are saying that you don't measure distance, straight line
Yes,
distance,
like
you're
this.
measuring.
Yes.
So there must be some change in the way we have taken care of the separating line. So so dividing the problem into two parts, that is not going to be a problem. But then merging the two solutions, that means
Yes.
checking whether there is a cross solution, that will require more thought and more details to be added. So let's give it a thought. Let us say there's a point here, there's a point here. This is a separating line. Let us also say that, okay, on the left side, the smallest Manhattan distance is okay. So for the sake of the larger audience, the question is that if we do not measure distance between 2 points as the straight line distance, but if we go along the x-axis and go along the y-axis and what is called the Manhattan distance, then will the algorithm still work, or there's some tweaking is required, or it will not work at all? Like I said, this is the other side. This is G2. So what I think is the crux of the algorithm, that this merging step can be done in linear time. That we should be able to justify that how we will justify the linear time merging. So for every point, we should be able to compare only with the constant number of points, and that should be sufficient. And how we should prove it in this case. So the previous argument is that, like the one that you have seen in the blog, that if there is a point in this grid cell, then you don't need to compute distance of this point with something which is here, because in between there is a d/2 d gap already. You read it. So this is a strip of width d. This is also width of strip of width d, and these grid cells are d/2 cross d/2. And since grid cells have length d/2, the length of two consecutive grid cells is already d. So therefore, if there's a point here, you don't need to check it with a point here, because then the distance would anyway be more than d, where d is the minimum of d1 and d2.
D line.
So can it so happen that you have to look at a point which is very far from this point and still it achieves a very small Manhattan distance? That is probably not possible, right?
No, that will be the triangle inequality. It will be. It is not possible, right?
Yeah,
The short- It will
I
only
think
be
so.
longer.
I think so, because see the distance, for example, let us take the triangle. So let us say that I have 2 points, let us say P1 and P2, and there is a Euclidean distance between them, and of course there is also a Manhattan distance between them. So let us say this is base, this is perpendicular, this is height. So we know for a fact that h is
Smaller than
root
sum
over
of.
yes, but there is this function that means you want to so can I write P plus B, which is the Manhattan distance, in terms of h alone? Can I write it as a function of h? Oh, I see, I see, I see. So consider the circle with P1, P2 as the diameter. Okay. So now you know for a fact that if you take a point on the perimeter of this circle, you take a point on the perimeter of this circle anywhere and join P1 and P2 to this point. Okay, let's call this point Q. Then these two chords that you have drawn, these two black chords. So the sum of the squares of the length of these two black chords is anyway going to be h squared, right? So whether it is like this, it is like this, it does not really matter, because of the fact that all these triangles are right angle triangles. So the angle here is 90. Are you with me?
Yes, yes, I am following.
Okay. So I think now the question is whether, oh, then there is a problem, right? So now I do not know whether this, if I draw another triangle, which is very close by this, something like this, and this is, let us say, P dash, and this is P dash. So it could very well be possible that P dash plus P dash is not equal to P plus P. So along with H, something else also. So anybody has any thoughts? So I'll give it a thought offline. You also give it a thought offline that whether this algorithm can be tweaked when we measure distances as Manhattan distances. And then we can discuss it again tomorrow.
Okay, so for Manhattan distance, we have to evaluate more points, right? That is the one thing that I can get.
We have to evaluate more points, but I do not see whether it is constant number of points or
Okay.
it is some function of n.
Okay. Okay.
Thanks. It's a good question to think about. So there's a message on the text chat. Let's see that. People are saying that I'm not sure if this helps, but the metric space R to the 2 with respect to both spaces are homomorphic as MS. What is the full form of MS? Metric space, okay.
I could not follow Deepak, but I will think more.
Yeah, I also could not follow it the way it's not competent enough to understand the statement maybe. Okay, I'll ask people and I'll also try to give it a thought. Thanks, Deepak, for your observation. I don't know. It might help. Okay, so I'll upload this lecture note. I'll make one more tab here and I'll upload lecture notes, and videos will take like a couple of days. But yeah, please check the website. I will upload the material soon. Okay. So are there any more things to talk about today? Okay. All right. All right then. I wish you a good night and see you tomorrow. Take care.
Thank you so much.
Thank you, sir.